Ever felt like you're trying to thread a needle with, I don't know, a rope? Or maybe like you're searching for just one specific grain of sand on a huge beach, but you only want the red one, and like 96% of the beach is covered in white sand. Well, imagine trying to do that, but at the molecular level. And instead of sand, you're trying to catch millions of tons of greenhouse gases, specifically carbon dioxide, CO2 coming out of power plant smokestacks, where it's all mixed up with mostly nitrogen. And the solution might actually be found in something surprisingly common, but incredibly complex when you zoom way in. We're talking about specially designed carbon. Welcome to the deep dive. This is where we take cutting-edge research, pull out the really important bits, and we'll make sense of it all for you, our curious listener. Today, our mission is to dive headfirst into a brand new research paper, one that might just revolutionize how we approach clean energy. It's all thanks to some, frankly, ingenious molecular architecture. We're going to explore how these specially designed porous carbons could radically transform CO2 capture from industrial emissions. And to guide us through this pretty intricate world of molecular sieves and designer pores, we have our expert with us today, ready to connect the dots for us.
Thanks. Yeah, it's a fascinating topic. The big problem we're tackling today, it's really one of the most significant environmental and frankly economic challenges we face right now. It's this urgent need for really energy efficient CO2 separation from industrial flue gases.
Flue gases.
Yeah.
So the stuff coming out of smokestacks.
Exactly. And we're often looking at really big sources like natural gas combined cycle power plants, NGCC plants, they're called. Now, these plants are super efficient for making electricity, but they still produce a lot of carbon dioxide.
Right.
And capturing that CO2 efficiently, before it hits the atmosphere, that's absolutely crucial if we want to meet climate goals and move towards cleaner energy.
Right. Makes sense.
So for a long time, porous carbons have looked really promising here. They're relatively cheap to make, they're incredibly stable, even under the harsh conditions inside a power plant flue. And at least in theory, you can tune their properties.
Okay, so cheap, stable, tunable. Sounds ideal. What's the catch?
Well, that's the core challenge this new paper really dives into. Making these carbons super selective for CO2, meaning they grab only CO2 and let everything else, mainly nitrogen, pass by. And doing that without losing efficiency, meaning without reducing how much CO2 they can actually hold, that's been a huge hurdle, a real sticking point in material science for years.
Okay, so you want it to be picky, but also have a big appetite, basically.
Precisely. It's like trying to design a filter that's incredibly specific, but also incredibly fast and can handle enormous volumes without getting clogged or slowing down. This paper offers a really fresh perspective on how we might finally strike that balance.
Okay, let's unpack that problem a bit more then.
Yeah.
Because understanding the challenge really helps appreciate the breakthrough, right?
Yeah.
We know activated carbon is great at grabbing stuff. Like my water filter at home uses it, some air purifiers too. They're basically molecular sponges, yeah.
That's a good analogy. They have these millions of tiny pores, creating a massive internal surface area that can trap impurities, adsorb molecules.
But capturing CO2 from a power plant, where it's maybe only 4% CO2 and like 96% nitrogen, plus other stuff, that's not just about having a big sponge. It feels more like trying to catch one specific type of fish in an ocean absolutely teeming with another type that looks almost identical.
Exactly. And you need to grab only that target fish, the CO2, let all the nitrogen swim by, and do it incredibly cheaply and efficiently on a massive industrial scale.
Yeah, that sounds tough.
It is. And you've really hit on the fundamental difficulty. For decades, the traditional way of trying to design these carbons ran into what you could call a molecular catch-22. The problem was that the carbon's chemical properties, like how much nitrogen you try to incorporate into its structure.
Nitrogen. Why nitrogen?
Good question. The idea was that nitrogen atoms embedded in the carbon structure would act like little chemical magnets, helping to attract CO2 molecules. We call that N-doping.
Okay, so N-doping for chemical attraction. Got it.
Right. But the problem was that chemical property, the nitrogen content, was almost always linked to the carbon's textural properties. Things like the total surface area, the size of the pores, how they're distributed, those physical characteristics that determine how much gas it can actually hold.
So changing one messed up the other.
Pretty much. Imagine baking a cake where, I don't know, the amount of sugar controls both the sweetness and the fluffiness, but in opposite ways. Add more sugar for sweetness, the cake gets dense. Try to make it fluffier, maybe by adding less sugar and it's not sweet enough. You couldn't optimize both at once.
Okay. That's frustrating.
Extremely. So researchers would try N-doping to boost the CO2 attraction, and it worked, a little. But the process of adding that nitrogen often unintentionally reduced the overall pore space. Or it changed the type of pores you got in ways that weren't helpful.
So you'd get stickier carbon, maybe, but with less room for the CO2 to actually stick to.
Exactly. You might gain a bit of chemical selectivity, but you'd lose overall capacity, or you wouldn't get the right kind of physical structure, the right pore sizes for efficient capture. It was this constant, frustrating trade-off. And that's really held back porous carbons from competing with other, often more energy-intensive capture methods.
Okay, that molecular catch-22 really paints a picture. Years of hitting that wall.
Yeah.
So if the old way was this balancing act you couldn't win, what's the game changer here? What was the big idea that let this team break through? This is where dual-cation activation comes in. Sounds very sci-fi lab.
It does sound fancy, but it's a really clever approach that tackles that catch-22 directly. The breakthrough comes from a team, let's give them credit, including J. Aaron Eichler, James N. Burrow, and C. Buddy Mullins. They're at the Department of Chemistry and Chemical Engineering at the University of Texas at Austin. And they collaborated with Rui PPL Ribeiro from Nova University Lisbon in Portugal. They published their findings in a top journal, Advanced Functional Materials. And their big innovation is this new way of making the carbons, which they call dual-cation chemical activation.
Dual-cation activation. Okay, break that down for us. What does that mean?
So think about making activated carbon. Usually you treat a carbon source with a chemical activating agent, often a type of salt at high temperatures. This agent essentially etches away parts of the carbon, creating the pores.
Like a chemical drill, sort of?
Kind of, yeah. Or maybe like a sculptor's chisel. Now, traditionally, people used one type of salt, one type of chisel. What this team did was brilliant. Instead of just one salt, they used precisely controlled mixtures of two common, cheap alkali salts. Sodium carbonate, that's like washing soda, and potassium carbonate.
Okay, so using two chisels together, why does that help?
Because these two cations, sodium Na+ and potassium K+, behave slightly differently in how they interact with the carbon and create pores, especially depending on the carbon precursor. By using mixtures, they found they could modulate porosity independently of nitrogen content. That's the key phrase. That's the decoupling they achieved.
Ah, they broke the catch-22.
Exactly. For the first time, they could make carbons with very similar nitrogen levels, so roughly the same chemical stickiness, but with vastly different internal pore structures. They could tune the pore sizes, the surface area, all that textural stuff, without messing up the nitrogen content and vice versa.
So, back to your cake analogy. They found a way to control sweetness and fluffiness separately.
That's a perfect way to put it. They can now bake the perfect cake, tailored exactly how they want it, without those old trade-offs.
That's huge. Okay, so how do they actually do it? What's the recipe for these designer carbons in a nutshell?
Right, the synthesis,
Yeah.
it's quite elegant conceptually. They started with precursors that are easy to get. Basically, carbon-rich materials made from sucrose, plain old sugar mixed with melamine.
Melamine, like in dishware.
The same basic compound, yes. It's very rich in nitrogen. So by varying the amount of melamine mixed with the sugar, they could precisely control the initial nitrogen content of their starting material before activation. They called these precursors SMX carb, where X just represented the melamine percentage. And that starting nitrogen level turned out to be really important.
Okay, sugar and melamine. Then what?
Then they soaked or impregnated these precursors with their carefully prepared mixtures of sodium carbonate and potassium carbonate. The exact ratio of sodium to potassium was varied systematically. That was key to the dual-cation part.
Got it. Soaking in the magic salt mixture.
Then, the crucial step, high temperature treatment. They heated the salt-soaked precursor to 800 degrees Celsius. That's pretty hot. And they did it under an inert argon atmosphere, so it wouldn't just burn up.
And that's when the salts do their work, carving the pores.
Exactly. At that temperature, the alkali salts react with the carbon structure, creating the porous network. It's the activation step. After it cooled down, they just thoroughly washed the material to remove all the leftover salts and any byproducts. What's left is the activated porous carbon ready for testing.
Okay, but you said the dual-cations allowed tuning. How does mixing sodium and potassium actually control the pores?
This is where it gets really interesting. It turns out this activation process isn't just one mechanism. It triggers three main ways that pores can form. And crucially, which pathway dominates depends a lot on two things: that initial nitrogen content of the precursor, the SMX value, and the specific ratio of sodium to potassium in the activator mix.
Three different ways to make pores. Okay, what are they?
So, for the carbons that started with low nitrogen content, The main mechanism seems to be something called intercalation exfoliation.
Intercalation, like inserting something between layers.
Precisely. Imagine the carbon is like a stack of very thin sheets, like graphene layers, but maybe not perfectly ordered. We call that turbostratic carbon. The activating agent, especially potassium ions, which are larger, likes to wedge itself between these carbon layers. It intercalates. Then, at high temperature, it pushes the layers apart, kind of exfoliating them.
Like puff pastry, creating flaky layers with spaces in between.
That's a great visual. It tends to create larger pores and higher surface areas, especially with more potassium.
Okay, that's pathway one. Low nitrogen precursors. What about intermediate nitrogen?
For precursors with intermediate nitrogen content, chemical etching becomes more significant. Here, the activating salts don't just push layers apart. They actually react chemically with the carbon atoms themselves, essentially dissolving or etching away parts of the carbon framework to create pores and channels.
So less like separating layers, more like carving tunnels.
Exactly. Think of it like using a chemical to etch patterns onto a surface. It's a more direct way of carving out the pore space.
And the third pathway, for the high nitrogen stuff.
Right. For the precursors starting with high nitrogen content, the dominant mechanism seems to be salt templating. In this case, the molten alkali salts, especially the smaller sodium ions, seem to play a big role here, can actually form tiny crystalline structures within the carbon matrix as it's being formed. They act like a temporary mold or a template.
A mold made of salt.
Yeah, the carbon forms around these tiny salt structures. Then, when you wash the salts away at the end, they leave behind perfectly formed pores that mimic the shape and size of the salt template.
Wow. So you're basically casting the pores using salt crystals.
That's the idea. It allows for the creation of very specific, often smaller, pore sizes.
So let me get this straight. By choosing the starting nitrogen level and tweaking the sodium-potassium ratio, they're essentially choosing one of these three pore-making processes. Exfoliation, etching, or templating is going to be the main one.
That's exactly right. They're not just randomly creating pores anymore. They are, in effect, programming the pore formation process.
That's genuinely like being a molecular architect, designing the internal landscape of the carbon.
It is. It's an unprecedented level of control. And that ability to tailor the physical structure, the pore architecture, independently from the chemical nitrogen content, that's the real breakthrough, that's how they overcame that old molecular catch-22.
Okay, so they've got this amazing new recipe, this dual-cation activation, letting them play architect at the nanoscale, designing these carbon structures with incredible precision. But, the proof is in the pudding, right? How do they actually know it worked? How do you look inside a tiny speck of carbon and see if those blueprints turned into the real thing? What kind of microscopic detective work do they have to do?
That's absolutely critical. You can have a great design, but you need to verify it. So the team used a whole suite of advanced characterization techniques to see exactly what they'd made. First off, to prove that independent control idea, they meticulously measured the final nitrogen content in all their different activated carbons, and the results were really clear. No matter what sodium to potassium ratio they used in the activator salts, the final nitrogen level in the carbon stayed remarkably consistent for any given starting precursor.
So changing the salts didn't accidentally change the nitrogen level.
Exactly. For instance, if they started with a low nitrogen precursor, low X and SMX carb, the final carbons always had around 2.3 atomic percent nitrogen, give or take a bit. If they started with a high nitrogen precursor, the final carbons consistently landed around 23 atomic percent nitrogen.
Okay, so check one. They definitely decoupled nitrogen content from the activation process.
Right. That was crucial confirmation. Then, to actually map the internal doorways and rooms, the pore architecture, they used techniques like X-ray diffraction or XRD.
XRD, that tells you about the structure, how things are arranged.
Yeah, it gives you information about the spacing between those carbon layers we talked about, the overall crystallinity, things like that. And, maybe most importantly, they used gas porosimetry. Usually with nitrogen gas, but also with CO2 itself.
Porosimetry, measuring cores, how does that work?
Essentially, you expose the carbon sample to a gas, like nitrogen, at very controlled temperatures, usually very cold, liquid nitrogen temperature, and you measure precisely how much gas sticks to the surface, how much adsorbs at different pressures.
Okay.
By analyzing how the amount of adsorbed gas changes with pressure, that gives you something called an absorption isotherm, you can use mathematical models to calculate things like the total surface area, the total pore volume, and crucially, the distribution of pore sizes. How many small pores, how many medium, how many large.
Like taking a CT scan, but using gas molecules to map the insides.
That's a really good way to think about it. And what these molecular CT scans revealed was fascinating, and it really depended on that starting nitrogen content. For the N-pore carbons, the ones starting with low nitrogen, they found that using more potassium in the activator mix led to some truly enormous surface areas.
Wow, enormous.
Up to 4,300 square meters per gram.
Wait, 4,000? That's insane. Isn't that like a football field packed into a tiny bit of powder?
Pretty much, it's a colossal internal surface.
Hmm.
These potassium-rich activators also tended to create larger micropores and mesopores, plenty of room. But interestingly, fewer of the ultra-tiny pores.
Okay. And what if they use more sodium with those N-pore carbons?
Generally, more sodium with the N-pore precursors resulted in smaller overall surface areas, so a clear difference depending on the cation.
Now, what about the N-rich carbons? Did they behave the same way?
No, and this really highlights the tuning capability. For the N-rich starting materials, the trends kind of flipped. Here, using more sodium in the activator actually led to larger surface areas up to around 675 square meters per gram. Still very high, though not as astronomical as the N-pore potassium ones. But here's the really critical part. For these N-rich carbons, the sodium-rich activation significantly increased the volume of both ultramicropores.
Ultramicropores. Those are the really, really tiny ones,
The
right?
tiniest, yes. Bose pores less than 0.7 nanometers in diameter, so sodium boosted those. And it also boosted the slightly larger mesopores.
So different starting material, different activator mix, completely different internal landscape. They really could tailor it.
Precisely. They demonstrated they could manipulate the activators to sculpt vastly different architectures depending on the precursor's nitrogen content.
Okay, you keep emphasizing these ultramicropores. You said less than 0.7 nanometers. That sounds absurdly small. Why is that specific size so incredibly important for capturing CO2 and ignoring nitrogen?
This is really the heart of the selectivity mechanism they uncovered. It's the wow factor. And it comes down to basic physics molecular sieving. Remember, they found that sodium-rich activators, especially with N-rich precursors, were great at creating these ultramicropores, pores smaller than 0.7 millimeters. Now let's put that scale into perspective. A nitrogen molecule, N2, which makes up most of the flue gas and is the molecule we want to exclude, has a kinetic diameter of about 0.364 nanometers.
Okay, 0.364 nanometer for nitrogen.
And a carbon dioxide molecule, CO2, the one we want to capture, is slightly smaller. Its kinetic diameter is around 0.33 nanometers.
0.33 nanometers for CO2, so they're really close in size.
They are. The difference is tiny, only about 0.034 nanometers. But at this scale, that tiny difference matters hugely. What the researchers realized is that many of the ultramicropores created by their method are just barely big enough for a CO2 molecule, 0.33 nanometer, to squeeze into, but they are effectively too narrow, too constricted for the slightly larger nitrogen molecule, 0.364 nanometer, to enter easily or efficiently.
No way. So it's like a doorway that's exactly CO2 size, but just a fraction too small for nitrogen.
That's exactly the concept. Imagine a turnstile at a subway station. If you're the right size, you slip through. If you're carrying a slightly bulky backpack, you get stuck.
Wow. Okay, so it's not about chemistry like the nitrogen doping attracting CO2. It's just physical size.
It's primarily about the physical size constraints. They termed this size-sieving porosity. The pore itself acts as the selector, based purely on molecular dimensions. This is a fundamentally different way of achieving selectivity compared to just relying on chemical affinity.
That is incredible. Separating molecules based on differences smaller than a single chemical bond. That's mind-blowing precision.
It really is. And it forced them, and the whole field really, to rethink some long-held assumptions.
Like what assumptions did this challenge?
Well, a big one was the focus on beat surface area. For years, the goal in making adsorbents was often just maximize the beat surface area. The thinking was more surface area means more places for gas to stick, so more capacity.
Seems logical.
It does, but for dilute CO2 capture, like from flue gas where CO2 is only a small fraction, this research showed that EPA surface area alone is actually a poor predictor of performance.
Really? So having that football field of surface area isn't the most important thing?
Not necessarily for selectivity. You can have a massive surface area, but if all the pores are too large to distinguish between CO2 and N2, it won't be selective. It's not just about how much surface you have, but about having the right kind of surface specifically, having enough of those perfectly sized ultra-micropore doorways.
Quality over quantity for the pores.
Exactly. It's about the architecture, the quality of the porosity, not just the total amount. That's a fundamental shift in how we should think about designing and evaluating these materials for this specific application.
Okay, so we've got these amazing designer carbons. They have these tailor-made, ultra-tiny pores that act like molecular bouncers. CO2 gets in. Nitrogen mostly gets turned away because it's just a fraction too big. It's like an exclusive club designed only for CO2 molecules. So how do the molecules actually behave once they encounter these surfaces? Is it just a chaotic scramble, or is there more to the story, like how strongly they stick?
It's definitely more nuanced than a scramble. It's more like an elegant molecular dance governed by thermodynamics.
Hmm.
And understanding that dance was another key part of this research. Using sophisticated modeling techniques, specifically something called a multi-site Langmuir model, they were actually able to identify three distinct types of parking spots or adsorption sites for CO2 on these carbon surfaces.
Three different kinds of spots for CO2.
Yeah, they labeled them alpha, beta, and gamma sites. Each one represents a slightly different energetic environment for the CO2 molecule when it adsorbs.
Okay. Which one is the most important?
The alpha site, think of this as the VIP section. This site showed the strongest attraction, the highest binding energy for CO2. And that's incredibly important for flue gas capture because the CO2 concentration is low, maybe only 4%. You need sites that can grab CO2 really effectively, even when it's sparse.
Makes sense. Where are these alpha sites found?
They found that the capacity of these alpha sites strongly correlated with the volume of pores smaller than 0.37 nanometers.
Smaller than even the nitrogen molecule.
Yes, we're talking about the absolute narrowest spaces. This dimension is very close to the typical distance between stacked, somewhat disordered carbon layers, what we call turbostratic carbon sheets. It suggests the CO2 molecule might be interacting strongly with two pore walls simultaneously, fitting snugly in that interlayer space, like being held in a precise molecular embrace.
It's a really tight fit.
Exactly. And these superselective alpha sites were most abundant in those N-rich and N-intermediate carbons that were made using the sodium-rich activators, the ones best at creating ultramicropores.
Okay, so alpha sites are the VIP spots in the tiniest pores. What about beta and gamma?
The beta sites correlated with slightly larger pores, maybe in the range of 0.37 to zero point 0.8 nanometers. Here, the CO2 interaction is still significant, but maybe less intense, perhaps interacting strongly with only one pore wall on average. And the gamma sites were associated with even larger pores, above roughly 0.85 nanometers. While these sites exist, the modeling showed their contribution to CO2 uptake at the low pressures relevant to flue gas was basically negligible.
So for practical purposes, it's really all about maximizing those high-affinity alpha sites in the ultramicropores.
That's the key takeaway for CO2 adsorption, yes. Now, let's contrast that with nitrogen, the molecule we don't want to capture.
Right, the unwanted guest.
Yeah.
How does N2 behave?
Well, first, unlike CO2 with its three distinct sites, nitrogen seemed to show only a single, less specific type of adsorption site across all the different carbon samples. It doesn't seem to find those special VIP spots. And here's another critical finding. Remember how they controlled the initial nitrogen content in the precursors?
Yeah, the SMX value.
They found that increasing the carbon's nitrogen content, going from N-poor to N-rich precursors, actually significantly reduced the amount of N2 that adsorbed.
Wait, more nitrogen in the carbon means less nitrogen gas sticks to it? That seems backwards.
It does seem counterintuitive at first glance, but it
Right.
makes sense if you remember why those N-rich carbons are good. They are the ones, especially with sodium activation, that are rich in those ultra-small CO2 selective pores. So while adding nitrogen helps create the right structure for CO2, that same structure is inherently bad at adsorbing nitrogen, likely due to size exclusion and maybe other subtle electronic effects. They saw up to a 75% reduction in N2 uptake, going from N-poor to N-rich samples.
Wow. So the N doping helps build a CO2 club, which inherently keeps N2 out. That's clever.
It's a really elegant interplay between structure and function, but there's one more thermodynamic twist that's really fascinating.
Go on.
They looked not just at how much gas adsorbed, but how strongly it was held, thermodynamically speaking. They measured the enthalpy of adsorption, that's basically the stickiness or the energy release when a molecule binds. And here's the surprising part. The enthalpy, the stickiness for N2 and CO2 on these sites was actually remarkably similar.
Similar. But I thought the whole point was that CO2 sticks better.
But enthalpy is only half the story in thermodynamics. The other crucial factor is entropy.
Entropy. It's like disorder, randomness.
Exactly. Think of it as a measure of a molecule's freedom of movement. Gas molecules flying around have high entropy, lots of freedom. When a molecule adsorbs onto a surface, it gets stuck, it loses a lot of that freedom. That's a decrease in entropy, which is thermodynamically unfavorable. It's called the entropic penalty of adsorption.
Okay, so sticking to the surface costs the molecule some freedom, some entropy.
Right, now here's the thermodynamic twist. The researchers found that the entropic penalty for N2 adsorption was much greater than for CO2 adsorption in these tight pores.
N2 loses more freedom than CO2 when it tries to stick. Why?
That's a great question, and the exact molecular reasons are complex, possibly related to rotational freedom or how the molecule fits. But think of it like this. Imagine trying to get comfortable in a very tiny, confined closet. Maybe CO2, being slightly smaller or interacting differently, finds it somewhat acceptable. It loses freedom, but it manages. But N2, maybe it feels much more trapped or restricted in that same tiny space. It loses more of its preferred state of freedom compared to CO2. It experiences a significantly higher entropic penalty.
So even if the glue holding them, enthalpy, is similar, N2 feels much more uncomfortable being stuck there. Higher entropy cost.
Precisely. And thermodynamics always favors the path of least resistance, the lowest overall energy state, which includes both enthalpy and entropy. Because N2 suffers this larger entropic penalty, it's just much less likely to stay adsorbed compared to CO2, even if the initial attraction is similar. The overall process favors CO2 adsorption over N2 adsorption.
That's subtle but powerful. It's not just about attraction. It's about how much freedom the molecule loses by sticking.
Exactly. This entropic discrimination is a key part of why these materials are so selective. It's a beautiful example of how subtle thermodynamic differences can be exploited for highly effective separations.
Okay, so we've got these designer carbons with ultra-precise pores acting like molecular sieves. We know CO2 gets VIP treatment in the tiniest alpha sites, thanks partly to that size exclusion, and partly because N2 hates losing its freedom, the entropic penalty.
Yeah.
This is a fantastic scientific story. But does it actually translate into performance that's good enough for, say, a real power plant? Are these materials just cool in the lab, or could they actually work in the real world?
That's the crucial question, and the results here are genuinely exciting from a practical standpoint. The team used a standard theoretical method called ideal adsorb solution theory, IST, to predict how these materials would perform, separating a realistic flue gas mixture.
IST, that's like a simulation of the real separation process.
It's a well-established predictive model based on the single gas adsorption data we just discussed. They simulated a typical flue gas from a natural gas power plant, about 4% CO2 and 96% N2. A challenging separation.
And what's the target? How pure does the CO2 need to be?
For a capture process to be considered viable for things like geological storage or utilization, the industry generally looks for the captured stream to be over 90% pure CO2. In terms of this IST model, that purity target translates to needing a selectivity value of greater than 216.
Okay, 216 is the magic number for selectivity. Did they hit it?
They didn't just hit it, several of their samples, particularly the N-rich ones made with sodium-potassium mixes, blew past it. The best performing material, which they called SM80AG and A0.5K 0.5, meaning it started with 80% melamine precursor and used a 50-50 sodium-potassium activator mix, achieved an IST selectivity of 275.
Wow, 275. So significantly better than the benchmark needed for practical use.
Absolutely. That indicates it could produce a very high purity CO2 stream, which is exactly what's needed. And this brings us back to the core revelation, the big aha moment from their work. Their results strongly showed that this high selectivity was almost entirely driven by the relative porosity, the specific pore size architecture they engineered.
So it really is all about the designer pores.
Mostly, yes. It's not primarily about the nitrogen atoms chemically grabbing CO2, which was the prevailing wisdom for a long time. Now, the nitrogen doping is important, but its main role seems to be enabling the formation of those crucial ultra-small CO2 selective pores and simultaneously reducing the number of pores that N2 can easily get into.
So the nitrogen helps build the perfect physical structure, rather than acting as the main chemical hook itself.
That's what the evidence strongly suggests. The selectivity is controlled by having the right size doorways that physically discriminate between CO2 and N2, leveraging both size exclusion and those entropic effects. It's physics leading the way, with chemistry playing a vital supporting role in creating the right physical stage.
That's a huge shift in thinking, focusing on building the right space, not just the right stickiness.
Exactly. And they also found another practical knob to turn.
Oh yeah, what's that?
Temperature. They found that simply increasing the operating temperature of the adsorption process could further boost the CO2 purity.
Higher temperature makes it more selective. How does that work?
It goes back to that entropy penalty for N2. Remember, N2 hates being confined more than CO2 does. At higher temperatures, molecules have more energy, they're bouncing around more vigorously. Under these more energetic conditions, that entropic discomfort for N2 becomes even more pronounced. It's even less likely to stick compared to CO2 when things heat up.
So warming things up shakes the N2 off more easily than the CO2.
In essence, yes. Now, doing this comes at a small cost. You might capture slightly less CO2 overall, lower capacity, at the higher temperature, but it gives engineers another way to fine-tune the process. They can balance the required purity against the desired capacity, depending on the specific application or economic factors.
Another control dial. That's always good for engineers.
Definitely. And just to underscore how significant this is, the best carbon material they synthesized showed a 147% larger CO2 capacity.
Double and a half the capacity.
And over 2,000% larger selectivity compared to a standard commercial activated carbon benchmark they tested.
2,000%. That's not an improvement, that's a transformation.
It's a massive leap for this class of materials. And importantly, its performance was comparable to some of the current state-of-the-art materials like metal organic frameworks, MOFs, and zeolites.
MOFs and zeolites, those are the really fancy, highly engineered crystal structures, right?
Yeah.
Often seen as the gold standard.
They're often considered benchmarks due to their precise ordered pores. But activated carbons, like the ones developed here, have a potentially huge practical advantage: cost, especially regeneration costs.
Regeneration, you mean getting the CO2 back out so you can reuse the carbon?
Exactly. Capturing the CO2 is only half the battle. You need to release it efficiently to store or use it, and then reuse the adsorbent material thousands of times. This release step usually requires energy, often in the form of heat or pressure changes. Because these carbons rely on relatively weak physical adsorption, adsorption, like molecular Velcro, it generally takes much less energy to release the CO2 compared to materials where CO2 binds more strongly chemically.
Weaker bond, easier release, less energy needed.
Right. MOFs and zeolites sometimes involve stronger interactions. Plus, activated carbons are generally known to be more robust and stable, especially in the presence of water vapor, which is always present in real flue gas and can be a major problem for some other materials.
So potentially cheaper to run, especially in real humid conditions.
That's speculation and a major driving force for developing better carbons. Lower regeneration energy translates directly to lower operating costs, which is absolutely critical for making carbon capture economically viable on the massive scale needed for power plants.
This sounds incredibly promising then. What are the next steps? Where does the research go from here?
Well, this work really opens the door. The immediate next steps involve testing these best-performing materials under more realistic conditions, using actual simulated flue gas mixtures that include not just CO2 and N2, but also oxygen, maybe some sulfur oxides, and critically, water vapor to see how they hold up. And then the crucial step is integrating these material properties into full-scale process models. That allows engineers to simulate the entire capture plant, calculate the real energy requirements, the actual working capacity over many cycles, and estimate the overall cost much more accurately. But this isn't just incremental progress. It's a significant, actionable step built on a fundamental shift in understanding, pushing us much closer to practical, affordable, and scalable clean energy solutions.
Okay, let's try to wrap this up. What does this all mean for us looking towards, hopefully, a cleaner energy future? This deep dive into this work by Eichler, Mullins, Ribeiro, and their colleagues, it feels like it's revealed some really big shifts. So takeaway number one seems to be, this dual-cation activation is like a powerful new toolkit for carbon architects. It lets them build porous carbons with unprecedented control, separating the tuning of the physical structure, those tiny pores, from the chemical nitrogen content. They crack the code on that old catch-22.
Absolutely. That independent control is fundamental.
Okay, takeaway number two. The secret sauce for super-selective CO2 capture isn't just about chemical stickiness from nitrogen anymore. It's mainly about physics. It's about having those perfectly sized molecular doorways, the ultramicropores, that physically block the slightly larger nitrogen molecules, combined with that subtle entropic effect where N2 just hates being confined.
Precisely. Pore architecture and thermodynamics are the stars here.
And takeaway three. These designer carbons aren't just theoretical wonders. They are showing real teeth. They're massively outperforming standard commercial carbons, and they're competing head-to-head with advanced materials like MOFs, But crucially, they might be cheaper to use in the long run because they likely need less energy for regeneration. That's huge for affordability.
That economic potential is definitely a major implication, yes. And if we pull back for the really big picture view, this research, I think, fundamentally refines how we understand physical adsorption in carbon materials. It powerfully demonstrates that by meticulously engineering the physical space at the nanoscale, the pore architecture, rather than focusing only on surface chemistry, we can create incredibly effective, highly targeted adsorbents. This isn't just tweaking an old recipe, it feels like a new design philosophy. A new principle for tackling one of the biggest environmental challenges we face, pushing us significantly closer to making large-scale carbon capture a reality.
It really does make you wonder, doesn't it? If we can learn to build materials with this level of nanoscale precision, creating these perfect molecular doorways for CO2, what other incredibly difficult separation challenges can we solve using similar ideas? Could we design pores to selectively grab pollutants from water, maybe microplastics or specific chemicals, with the same efficiency? Or could we apply this to other industrial processes, maybe filtering air or separating valuable gases? The possibilities seem vast once you unlock this level of molecular architecture. That's definitely something to think about. And that's all the time we have for this deep dive. Thank you so much for joining us on this exploration of some truly cutting-edge science.